Well, thank you very much, Scott, and the organizers for inviting me here to give a lecture. And I'd like to thank all of you for being here on a late afternoon on a Friday, right after the Raptors won. So I want to preface this by saying that I don't want to waste your time. I know some of you might rather be out celebrating. Some of you might be nursing a hangover. So I appreciate you coming out and listening to this, but I want to make this as enjoyable for you as possible and memorable. I was trying to calculate the number of talks that I have sat through in my career, and I have spent thousands of hours in lectures. And I would have to say that only a handful of them I probably remember anything about. And so I don't want to just regurgitate my research to you guys and then, we'll walk away an hour later, you wish that you had not come in here. You're trying to figure out how to sneak past your neighbors so you can get out inconspicuously. But rather, I thought about the different types of talks that really resonated with me and stayed with me over the years. And I think they had a few different attributes. And I'm going to try to hit on these key features so that you do not fall asleep. And I'm watching you guys to see if you do. So the first one is, I think, a lecture that I find intriguing makes me think outside the box. So I'm going to talk a little bit about some ideas that I've had. It also inspires me. Something that really resonates with me or stays with me long after the lecture has to inspire me. It teaches me something new, and it makes me laugh. I have been wanting to do stand-up comedy because I think that'll help my teaching evaluations. So I'm trying some new material out here, so I will gauge your reactions. So the first one makes me think outside the box. So I'm going to kind of tell you the story of my career, and in between I'll talk a little bit about my research. But so as Scott mentioned, I did my PhD at UC Berkeley under Luke Lee. So we made micro and nanotechnologies, doing a lot of microfluidics, lab on a chip. I don't need to introduce this audience to all of this, but we worked in a clean room, as many of you I'm sure do. And the idea was to make, these little chips that are very much like integrated circuits, available and inexpensive to the masses. And we started a company when I was about to graduate, Flexion Biosciences. It's in South San Francisco. And through that process, I just fell in love with doing startup companies. And so I had this opportunity to start a brand new university. So the University of California system has 10 campuses in total, and this 10th campus was just opening when I was graduating, and I got asked to be part of the founding faculty team. And so this is what my first faculty gig looked like when I arrived on campus. And I had no lab. I had to wear a hard hat onto campus, and they told me the clean room would be built in 2 to 3 years. So after staring at the cows for a while, and for you junior faculty, you understand the importance of publish or perish. And so I felt this. And they tell you it's this once-in-a-lifetime opportunity starting in a university because you would never want to do it twice. So after not having access to a clean room or any of the equipment that I was used to for my PhD to make these chips, I thought back to my fundamentals, right? What I was trying to do was to print things at very fine resolution so I could use that as a relief mask. I was trying to make these silicon wafers so that I can pour PDMS or an elastomer so that I can make the replica of it so I can make microfluidics. So I thought, well, if I can't pattern at very high resolution, what if I did the inverse? What if I patterned at the large scale and then shrunk everything down to the small scale? And so I decided, I was messing around in my kitchen one night, and I remembered back to my favorite children's toy. So this might be an American toy. You guys have shrink eatings here? Yes. You do. So it's a very specific age range that knows shrink eatings. I tried to explain to my students what shrink eatings are. I said, it's like overheads, and you can draw on them. They're like, what are overheads? So I found this video. This is what shrink eatings are. So shrink eatings are pre-stressed polystyrene sheets. So it's like a rubber band, and you draw on it, and then so they're pre-stressed, and then it's a shape memory polymer, so it just relaxes back to its native state when it's heated for 3 minutes in the oven. And so I thought, well, maybe this would be good enough to create the resolution that I needed. And if you think about it, when it shrinks in each direction by x, it grows in the z direction by x squared. So you get these really nice, deep, tall channels with high aspect ratios, and you actually got rounded channels, so it's actually really nice for valving also. So I was so excited. I was, a junior professor. I ran into the lab next day. I didn't have any graduate students at the time, so I told my undergraduates, and they're like, we can't publish on that. People would laugh at us. And so so to this day, this is still the workhorse of my lab. So we've, you can watch the word shrink, shrink. So it shrinks down to about 5% of its original pattern size. And we use this, and so we ended up getting a lot of press around it. We published this in Lab on a Chip, which is the leading journal in microfluidics, and the paper went viral. And to this day, it remains the workhorse in our lab. And we can pattern at the large scale. Now we made it compatible with standard photolithography, and we can put down different types of more exotic materials like graphene, carbon nanotubes, but we still can shrink everything down, so we get this very high surface area for given projected surface area. And so we've been doing a bunch of different things with this. And so one of the things you can do, you can imagine that if you put a stiffer layer on top, so if you put a metal, for example, on it, and the metal can't shrink, so it buckles, you can control the buckling, and you can control the wavelengths depending on the stiffness of the metal and the thickness that you put down. And so we've used this for, you can use this for surface enhanced sensing, such as surface enhanced Raman spectroscopy, metal enhanced fluorescence. We also did some far field types of amplifications because we wanted to do point of care. We really wanted to make these low cost solutions that we could bring out into the field. And so we put down silica, and we get these really interesting optical effects so that we can get very large enhancements. And like any good junior faculty, we published a bunch of papers. And as the last talk, Mohammed had talked about, there needs to be more impact than just papers. And so we really thought about, well, we have this really low cost solution, and it's compatible with roll-to-roll processing, so we could make these things for pennies. So, after these papers helped me get tenure and everything, I really thought, well, what is it that really inspires me? What is it that I want to actually do and change about the healthcare system? And so this leads me to the next area of my talk. And this is what we've been working on for the last couple of years. So this is, a picture, a schematic of a new car. And this isn't a fancy car. This is probably your standard Honda. But what's interesting about this is that the average new car has about 60 to 100 sensors on it, right? So it'll tell you everything from the tire pressure in your car to whether you're going to hit somebody when you're parking, which is very handy for me. The average new person, on the other hand, has 0 new sensors. And you can say, well, yeah, that's kind of obvious. That's par for the course. But if you think about this analogy, let's think about this a little bit more. On average, the average American keeps their car for about 6 years. And in that number of, drive it about 110,000 miles. Surprisingly, the average person in their lifetime also walks 110,000 miles. But the average person breathes over 827 million times and has over 2 billion heartbeats. And if you think about this, if you miss even a couple of breaths or a couple of heartbeats, that's game over, right? There's no calling AAA. And so, but there's nothing to monitor this. You don't wait until your check engine, you don't wait until you're stranded on the side of the road to get your car fixed. You have all of these sensors telling you what's going on at any given time. And so this really hit home to me a year ago. This was my son in the NICU. I had a scheduled C-section, and he aspirated on some amniotic fluid because he wasn't expecting to be pulled out, apparently. Apparently, this is very common in hospitals, that babies end up in a NICU after aspirating on amniotic fluid. He had a collapsed lung, and I wasn't allowed to carry him for 8 days. And all of these sensors, these EKG sensors, they give you respiration rate, and we'd watch these for 8 days. We watched these signals fluctuate. And we thought, oh, maybe his breathing is getting better because they told us his lungs had to heal before we could carry him. And then we asked the doctors after a few days, we're like, it looks like, you know, he's breathing deeper. And they're like, oh, never mind that. Those things are not calibrated. We have no idea what volumes he's breathing. There was no way to actually get minute ventilation in a NICU, in a leading hospital in California. And fortunately, this has a happy ending. My son just turned 1 a couple of weeks ago. But it really hit home this goal of mine to end system-based reactionary medicine. Right? We shouldn't have to wait until we're stranded at the side of the road. Physiological changes precede clinical deterioration. We notice. So why can't we monitor these? Why can't we do, as the previous talk talked about, take all of that data and be able to do something preemptively? And so my lab has been working on developing these sensors to be able to do that. We published this with a bunch of other authors, including John Rogers, Joe Wang. They work on different areas. Our area really is these mechanical sensors to be able to do on-body sensing. And the idea behind how we make these sensors is still very much in line with the shrinky-dinks. So we have these metal wrinkles. And the cool thing about this, that if you take those wrinkles off of that shrinky-dinks hard plastic and you put it into a soft polymer, the wrinkles actually, it's like an accordion. It allows you to stretch out the thin metal film really easily. And you can also control the gauge factor. So you can get a very high, so strain gauges have been around forever, right? You put them on buildings and they typically stretch 1 to 3%, and you get a very high signal to noise ratio. And you can tell if a bridge or a building is deflecting a little bit. And they've never had to stretch very far because on buildings they don't move very much, but on the body they do. But strain gauges that can stretch out that far typically have a very low gauge factor. And so what we discovered with our nanostructures was that we can get a very high gauge factor, but also a very large dynamic range. And what I mean by this is that you can stretch this out and you can see the electrical response. So we thought, well, maybe this is good enough to start monitoring physiological signals. And so one of the things that I was very passionate about monitoring was children's breathing. So asthma is the #1 chronic disease in children. And there's, you know, over 3,000 preventable deaths each year due to asthma. Nobody has to die of an asthmatic attack. But people wait because the child starts wheezing and they don't do anything about it until it's too late. You catch it early on. The symptoms include difficulty breathing, coughing, and a lot of this actually occurs at night. So, and if children or parents are not aware of all the symptoms, they end up having to go to the ER. And the longer you wait, the more progressive it gets. The current standard of care is to blow into a peak flow meter twice a day and manually track the volumes that your child is breathing at. And over the course of 40 days, you should start seeing a pattern emerge. It's very hard for a child to breathe maximally into one of these peak flow meters, and it doesn't actually give you any, you know, real-time predictive information. You can just start seeing a trend. So there's nothing continuous or automated about monitoring a child's breathing. And so we thought, well, what if we just made our little sensor and we put it right on the floating rib, and we had everything pushed to a smartphone, and we can monitor when the person is breathing, and we can even make real-time alerts, sort of like a Waze for breathing, if there are allergens in the area, you know not to take your child there. The other thing that it can do is also give a closed loop control for when your child has taken their medication. So you can actually tell how your child is responding to the medication. Because right now they have smart inhalers, but there's nothing that actually closes the loop to say, well, this is how you're reacting after your medication is taken. And so the first step was to compare this to the gold standard spirometry. So for this study, we put it's like a little Band-Aid. So we put one on the floating rib and one on the abdomen, and we compared it against standard spirometer. So we made a little model, and we got excellent correlations against the standard spirometer. So with 2 sensors, you can see that the R-squared values are very high, to over 0.9 for all of them. And even with 1 sensor, we're getting very high correlations against the spirometer for respiration volume. For respiration rate is actually a lot easier. There are technologies you can use an accelerometer to get respiration rate, but we can also track respiration rate very easily. So we published this in Nature Digital Medicine, and we got a little bit of press around that. And then we started looking at simulating asthmatic attacks. So we can also tell, just like a spirometer can tell, the difference between obstructed breathing and normal breathing. We simulated asthmatic attacks by obstructing breathing, and we can also see the similar trend with our sensors. And it's a very, the exhalation actually has a very well-defined profile for obstructed breathing. And now we are starting to do stimulated breathings with a collaboration with UCLA. So we have an IRB to actually do a methylcholine challenge to stimulate the asthma. So that's what we're out with that study. Switching gears a little bit, I wanted to talk about another sensor that we've been working on. And this one relates to cardiovascular disease. So cardiovascular disease is the leading cause of death globally. And it accounts for 1 in every 4 deaths in the US. The current standard that everyone, knows of is the blood pressure cuff, right? And everyone takes their blood pressure measurements, and most people probably think that it's a static measurement, right? When you take your blood pressure, you get a systolic value and a diastolic value. And that's what they use to define hypertension. But if you think about this, so using the basketball analogy again. So if you think about this, right, that blood pressure measurement is a static snapshot in time. And it doesn't give the whole picture, right? Is he going to make the shot or not? So it doesn't give you all the information, and your blood pressure is actually constantly fluctuating. And so that snapshot only gives you these 2 points. But what is actually important is that beat-to-beat variability. So that beat-to-beat variability is actually a better prognostic indicator of cardiovascular morbidity than just the cutoff of hypertension. But current blood pressure monitors are inadequate. They don't measure beat-to-beat blood pressure measurements. In fact, they don't look very different from when it was invented in 1881. But there are numerous studies indicating the importance of beat-to-beat blood pressure variability, not just for cardiovascular disease, but other diseases as well, even dementia and Alzheimer's. So a lot of these diseases have small vessel disease as kind of the underlying cause. And subclinical ischemia over years and years that go undetected ends up resulting in a lot of these diseases. So the gold standard right now, if you want to do beat-to-beat, is to do an arterial line. And the only time you really do that is when you're in the ICU, because it's invasive, you can't move at all with it. And so we've been developing a little Band-Aid-like sensor. This is a capacitive-based sensor based on the Shrinky-Dinks toy. So the idea behind this is it's like the strain sensor, except there's 2 electrodes with the polymers, the dielectric in between. And we've been comparing this with the standard. So for this first paper, we compared it against an FDA-approved device. It's the ClearSight by Edwards Lifesciences. It's what you use when you're in the ICU. It's a finger cuff based on a photoplasmography, PPG signal. And we've been able to back out absolute blood pressure and correlate this with the ClearSight. And we are well within ISO standards compared to the ClearSight device. And so we can monitor blood pressure continuously. And so we started a small clinical study on this to look at congestive heart disease. So the striking thing about congestive heart disease is about half of those who develop congestive heart disease die within 5 years of their diagnosis. And so if you catch it early on, it's very mild. If the longer you wait to go to a hospital, the more severe it gets. And most of the technologies on the market now wait until there's already fluid accumulation before it starts signaling it. So it looks at edema, for example. So we wanted to catch it early on, where we can actually look at hemodynamic parameters, changes in breathing that precede more advanced progression. And so one of the indicators of congestive heart failure is this Cheyne-Stokes type of breathing, and you can see this in one of our subjects here, where it's very periodic breathing. And you can also see how the blood pressure, I'm sorry, this graph did not come out so well, the blood pressure actually correlates with that quite nicely. The difference between healthy and diseased patients becomes quite obvious when you look at, for example, heart rate variability. So in congestive heart rate, in congestive heart failure patients, they have very little variability in their heart rate versus a healthy subject. And you can also look at things like systolic blood pressure variability. You see distinct differences between the low frequency parameters and the high frequency in terms of blood pressure variability. And we can also compare this against left ventricular ejection fraction. So typically you do an echo when you go into the clinic if you have congestive heart disease, and this is an indicator of how your congestive heart failure is progressing. And we've correlated that with systolic blood pressure variability. And we see so far, as a small cohort, we see kind of a nice correlation with that. So, we're kind of finding these interesting digital biomarkers so that these subjects can monitor their health and their progression at home without having to do so in the clinic. We also have developed, to go along with these physiological parameter sensors, we've been developing these electrochemical sensors to measure cortisol, for example, in sweat, glucose in sweat. And so using the same approach, we have pattern at the large scale, and then we shrink everything down to be very small so we retain all of that surface area. So we're noticing that we're getting about a 40x improvement in electroactive surface area compared to that projected surface area that you would get for that size. So onto the last part, teaches me something new. So I think there are quite a few students in the audience, and this is commencement weekend at UCI. So I wanted to think back about some of the lessons that I've learned over the years, and I thought what really kind of stuck with me and helped me. So just a couple of pieces of advice for the students. So the first hard-earned lesson learned is that you are capable of more than you can imagine, and to think big. And we always think that and then you can break everything down from there, right? But we always think that, you know, it's a straight line to get to where you want to go. But the path, when you look back, you realize it looks more like that, right? And so if you break down these tiny tasks, regardless of whether you're on this right path or not, you're getting closer and closer to your goal. It never is as easy as it sounds when you're looking forward, but looking back, you know, you realize it wasn't as bad either. Be yourself. Everyone else is already taken. When I started doing startups as a graduate student, I was told, do not do startups. Wait until you're a faculty member because it'll ruin your career. I was told not to go to UC Merced because it's not a top school. It'll ruin your career. You won't ever be able to get back to an R1 university. But I didn't listen to any of that advice. You have to just find your own path and go with it, and it'll work out. You know, at every step of the way, there will be people who tell you that it's not going to work out, or you know, you should do things the way they tell you to do it. But I think it's really important to stay your course and to be yourself. The next one is that. So the title for my talk is really, you know, I do a lot of outreach, a lot of STEM outreach, and I think the way we teach science to our kids is wrong. We teach them to do science, right? But we play sports, we play music. So there's this fun aspect to it, and losing is a part of just playing any sport, right? Nobody ever quits after they lose a game. And the best players, my 3-year-old son is obsessed with Steph Curry, they get up, right? He's lost so many times. Everyone told him he couldn't do this, he couldn't do that. But he just uses it as fuel, and he'll come back and win again. I'm sure that the Golden State will get another NBA championship. So failure is inevitable. And so I think we have to have that mindset with science. You know, a lot of these talks, we always talk about what we do right in our talks. And so the students just see, you know, positive results, but we don't talk about the thousands of experiments that never worked out. right? So I remember, so I have 6 companies. 2 of them like completely imploded. It was horrible. And I remember like crying in tears to one of my mentors who had founded Nelcor and Alere and a bunch of other companies that were, you know, worth well over, you know, $300 million. And he was in his 70s at this age, and I was just like, oh my goodness, I don't know what I'm gonna do. I'm never doing another startup again. And he just started laughing at me. I'm just like, why are you laughing at me? I'm pouring out my heart. I'm telling you, I'm miserable. I'm so upset. And he said, you know, you think that you're going over a cliff, but when you get to my age and you look back, you'll just realize these are just small little bumps in the road. And I guarantee you that will not be your last startup company. And he was right. I was just like, no, I'm never doing a startup again. He was just like, you say that now, but trust me, you will do it again. And he's right. So it may feel like you're going over a cliff at the time, but it really just is bumps in the road. The next one is to hug your fear monster. So I think a lot of us, especially as we get older and older, we're afraid to push ourselves outside our boundaries. But that's the only way you learn, right? Even with our research, we keep pushing into new areas. This wasn't the area I started in. I was doing microfluidics and lab on a chip, and I'm moving outside of my comfort zone. And so we have this little mantra at, you know, my house, and we say, you know, hug your fear monster. Because I started learning to skateboard when I was pretty old, in my 30s. And I remember the first time, my husband thought it was a good idea to take us to a skateboarding clinic. And so we went to the skateboarding clinic, which was run by like a bunch of 17-year-olds. And they take us down this like really, really big hill. And like, you know, this full I go and I start coming down a hill and I eat it. And I had like 10 stitches down, you know, my chin, and I had to be rushed to the emergency room and everything. And then the next day, my husband, my boyfriend at the time, was just like, let's go skateboarding. I'm like, are you insane? I just fell. Did you not see that? You were there with me yesterday. My face is still bloody. And he said, well, if you don't get back up today, you're not gonna get back on. And it's true. So I got back on and I skateboarded, but I think it's really important that we learn to really embrace our fears to get over them. You won't grow if you stay in your comfort zone. And when things don't work out as planned, it just means your plans suck. So I tell my students this, and they were like, thought this was this big aha moment. You know, they call it research for a reason. If you just search for it and you find it, you wouldn't have to research for it. It's research for a reason. So of course, you're not going to find your answers immediately. Good relations with your colleagues. I love this collaborative environment that you guys have created here. I think that that's really important to advance science because nobody does science in silos anymore. And then it's graduation season, so we always talk about, you know, the true key to happiness, and, you know, there's all these talks about finding your joy and finding what you find is really meaningful. And I know a lot of people who have been looking for that thing that's really elusive to make them happy. And when you have to do something every day, even your hobby doesn't make you happy all the time. And so I think that this is the wrong advice. I think the right advice is to do something that makes the world a better place. Give a little bit of yourself, and that's how you'll find your happiness. So with that, I love this quote, my ceiling gets to be the next generation's floor, and that is a great honor. So, and I will take questions.
Thank you, Michelle. Yeah, so we have, I think maybe like 5 to 10 minutes for questions. We'll take questions from the floor. Ori? Yeah.
So thanks for that inspiring talk. So one of the things we're trying to do here is bring together clinician scientists, and biomedical engineers. So you showed a lot of examples where your engineering was being tested in, I guess, patients or normal volunteers. So can you comment a little bit about the environment that you work in that makes it so successful?
That's a great question. That's an absolute excellent point, and I think that that is the way you actually make progress. We're very fortunate at UC Irvine to work very closely with clinicians. We work with pulmonologists for our respiratory sensor, and congestive heart failure physicians and stroke physicians on our blood pressure sensor. We've been working very closely with the medical school. I actually started a program called BioENGINE, which is bioengineering, innovation, and entrepreneurship, to have teams of students work on promising IP coming from the engineering school and the medical school to actually help develop those out a little bit more. So I don't think any of this can happen without the input of the clinicians. One of the companies is actually, one of my companies is actually being run by a clinician. So I think that close collaboration is really key to this. And I really am blown away by this environment here. I think that this is how good things happen.
Are you, is your lab group embedded in the hospital? Is the hospital right next door?
So we have physicians, so a lot of the physicians have, we have a clinic that is within walking distance from my lab. The main hospital is further away. It's actually about 20 minutes away, but we have the Beckman Laser Institute, which we do a lot of work over there. And then we have a lot of the other clinics on campus. So we walk in between, but I am actually in an engineering hall. We're gonna be moving over to, we're building a new interdisciplinary center, and our lab will be moving over there next year. So.
Question, how do you manage juggling so many companies with the lab?
So yeah, I'm involved to different degrees with the companies. I like the very early stages. Right now, I'm actually on sabbatical. I'm doing an entrepreneur sabbatical this year, which is really nice. So I get to spend a little bit more time working with the companies. But the university has been very liberal in, I've kind of, in my career, I've seen a complete shift where they told you before, not to do companies, especially if you're a junior faculty. Now, the dean actually had appointed me to be the director of faculty innovation to actually help faculty start companies. So it's very much shifting gears. And so they've been really great about letting me do that. So typically when I'm not on sabbatical, I'll dedicate a day a week to just work on a startup.
Question. So can you tell us a little bit about kind of your IP strategy and at which point decide that there's a company that can be formed out of your life?
That's a great question. So we write records of invention for everything. I tell my students it's just standard practice to file a record of invention before you publish. And then the tech transfer office will decide whether they're going to patent it or not. But we've been really fortunate that the tech transfer office has actually pursued a lot of the patents for us. In terms of when to kind of take it out of the lab, it's usually an outside person, so a CEO or some investors will come to us, and this has happened for the last 4 companies, has basically said, we'd like to license it and do a company around it, and that's when we decided, okay, it's time to spin it out. And I've been really lucky in that I've done a bunch of the startups with my students involved as co-founders, and so I think it's a really great experience for them, so that's kind of one of the motivations for doing the startups. So we've tested it on healthy, and we're right now testing it on congestive heart failure subjects. We've figured out how to calibrate it so we can get absolute blood pressure. We're developing out a way to remove the motion artifacts, and that processing is looking pretty promising. So right now we've done all of our measurements on static patients, so they're not moving during that time, but we've also are introducing movement into it, and we're able to get out the original signal with some confidence. We have, so we're in the process of spinning that out right now. We're working with a company, so there's a company that's doing a sponsored research project in my lab to kind of validate that as well.
Maybe one last question.
So the question was, I guess, some challenges that I've faced and how I've kind of gotten over that. So I guess, it's a good question. So I guess academically, the challenges that I faced when I was at Merced was, those 3 years, I always say those 3 years of my life were the hardest of my entire life. I think for any junior faculty, starting their career is difficult enough, trying to publish, trying to make a name for themselves, but when you're coming from a university with no infrastructure and no reputation yet, no name, that was really hard. On top of that, nothing was built, so we were on all of these committees trying to kind of juggle everything, and so I was trying to do my research basically in the middle of the night because, the day was filled with so much service work. And so it was really a matter of getting myself out of that situation. And fortunately, when I started publishing on some of these things and giving talks, then I started getting some job offers elsewhere. But I think it's just sticking with it and just figuring out a path out in terms of the companies. There's lots of ups and downs. For those of you guys who do startups, everything just feels amplified when you do a startup because there's always limited resources and tensions are high. And so I think it's keeping that perspective. Like when, one of my companies, we raised, almost $1 million. We were doing really well doing clinical studies. We got a Series A term sheet for $5 million. We thought, okay, finally, we're ready to go. And then that firm pulled their term sheet at the last minute, and the company ended up folding. And that was very painful because we had done all of this work, and then, within weeks, the company was gone. But that IP reverted back to the university. Another company and another group of investors came along with a more experienced CEO. They pivoted, found another better application for the technology and decided to pursue that. And so that's going well. So I think just knowing that, even if something completely doesn't work out the way you want it to, that you'll still be okay and there's still a path forward. So I don't know if that helps or answers.
Okay, so we'll thank Dr. Khine again for giving us this keynote lecture. And,